Hello everyone, I'm Guowei Yang from Texas State University, and I'm going to present our work on Redroid, a regression test selection approach for Android applications. Quang Du is my student who has recently graduated. This work is collaborated with Dr. Meiru Che, Darun Hui from University of Texas at Austin, and Jefferson Ridgway from Elizabeth City State University. Nowadays, mobile devices have become ubiquitous, and a great deal of research has been performed to improve the reliability of mobile apps on mobile platforms. Mobile apps are evolving over time, for example, to cope with new requirements or to fix bugs. And regression testing needs to be performed on the new versions of the mobile apps to ensure that changes are correct and do not adversely affect other features of the mobile apps. However, the majority of the research is focused on testing of a single version of the mobile apps. Although regression testing has been extensively studied for desktop applications, this approach cannot be directly applied to mobile apps. A key factor that causes this incompatibility is the system architecture difference between the mobile platform and the desktop platform. We conducted a study to investigate real-world Android bugs with an aim to find how these change-related bugs or regressions are manifested in Android apps. We selected Android apps from Google Code repository based on 4 specific criteria: large number of downloads, large number of bug reports, long development history, and a wide range of apps from different categories. So this table lists the 10 apps that were selected for this study. These 10 apps, chosen from 6 categories, have 2 to 6 years of history, and all of them have more than 50,000 downloads. All of these apps have more than 100 bug reports, and some of them have over 2,000 bug reports. By manually reading and analyzing each bug report, we found that regression bugs do exist in these apps. In particular, 15 regression bugs are found in Redroid. Note that our analysis may not find all regression bugs in these apps, as we require the bug reports to explicitly mention that the bug is caused by change, such as change to the app's source code, to a library, to app's configuration settings, or to hardware configurations. This study showed that there are regressions for Android apps during evolution, and an efficient and effective regression testing approach is highly needed for this area. This is an overview of our approach. There are 3 main components in the framework: impact analyzer, coverage generator, and test case selector. Impact analyzer generates impacted code that contains changes between the 2 versions. It first constructs control flow graph representations of the methods in the 2 app versions. Then it identifies pairs of anonymous inner classes for comparison between the 2 app versions. And finally, it uses the related work on deja vu algorithm to perform a simultaneous depth-first graph walk on a pair of control flow graphs to find the first impacted code along each path. Coverage generator computes the code that is executed by each test case. Existing tools such as Emmer are very useful and popular, but they do not provide coverage information for each test case. when a set of test cases is executed in one time, and thus are not suitable for this setting. Our approach uses instrumentation. It instruments each code block so that an instrumented code block is locked for a test when it is executed by that test. Test case selector takes as input the change impact information from impact analyzer and the coverage information from coverage generator, and selects for execution the test cases that are affected by the changes. This selection is conservative since any test that can potentially execute any changed block, any changed code block will be selected for execution. Next, I will use an example to illustrate our approach. A simple calculator, as shown in this figure, is a basic calculator. It takes two numbers as input and performs four arithmetic operations: addition, subtraction, multiplication, and division. Here shows the main part of the app's source code. 18 test cases are created to test the app's functionality. By running all the 18 test cases, 2 bugs are found in the original app, and 2 fixes are made to lines 4 and 22 where the operators are changed. After modifying an implementation, the app is required to be retested in order to assure that the 2 fixes remove the bugs that were found previously and do not adversely affect other program behaviors. Traditional approach simply re-executes all the test cases in the original test suite on the modified app. So traditional approach basically will re-execute all those 18 test cases. However, the modifications may not impact all those test cases, and simply rerunning all those test cases may not be an efficient way to check the modified app. Our approach, Redroid, combines change impact analysis and coverage information to reduce the number of test cases for re-execution, and only re-executes the test cases that can potentially reveal different behaviors from the original app version. So our approach first collects the coverage information of each test case. So it finds that lines 1 to 6 are covered by test cases T1, T2, and T3. Lines 7 to 12 are covered by test cases T4, T5, T6, and T7. Lines 13 to 18 are covered by test cases T8, T9, T10, T11, T12, and T13. Lines 19 to 24 are covered by test cases T14, T15, T16, T17, and T18. Moreover, it finds that lines 4 and 22 are changed. So combining the coverage information and change information, Redroid selects test cases T1, T2, T3, T14, T15, T16, T17, and T18 for re-execution on the modified app. So in this way, compared to the traditional approach, Redroid eliminates 10 out of 18 test cases for re-execution, which is a 55.6% reduction. Since our technique requires on the output of coverage generator, we first evaluate the efficiency and preciseness of the coverage generator by considering 2 research questions. How efficient is SEKE compared to the existing coverage analysis tool, EMMA? And does SEKE achieve the same level of preciseness compared to EMMA? We then evaluate the overall cost of Redroid relative to the traditional approach, which reruns all test cases by considering two research questions. How does the number of test cases selected by Redroid compare to the traditional retest all approach? And how does the time cost of applying Redroid compare to the traditional retest all approach? Although 10 apps were studied for our bug study, no tests were found for these apps. Thus, we select two other open source Android apps with test cases for evaluation: Identify and EndStatus. To evaluate our approach, we require multiple versions of each app. Because multiple versions of these apps were not available, we generated versions by manually creating mutants of the available app. When creating mutants, we consider a broad range of changes that could be applied to the code: change type, change location, and number of changes. The change types include modification, deletion, and addition of source code statements. Changes are introduced at different locations: control statements, non-control statements, general locations such as the top, middle, and bottom of the method, anonymous inner clause. Anonymous inner clause procedures are especially considered here because they are special Android features which are not existent in regular Java programs, and they are generated as separate class files by the Android development environment. In addition, each mutant has one, three, or five change statements. So this table shows more detailed information of each app. For each app, we created 5 mutants v1 to v5 with one change statement, 5 mutants v6 to v10 with 3 change statements, and 5 mutants v11 to v15 with 5 change statements for each version. Thus, in total, we created 15 versions for each app. This table shows the results of applying the two code coverage analysis tools, SEKE and EMMA. For each app, we list the total number of blocks, the number of executed blocks, the percentage of executed blocks out of the total blocks, and the time cost for coverage analysis, computed by SEKE and EMMA respectively. For RQ1, we found that for Identify, EMMA took 341 seconds to get the coverage information for each test case in the test suite, while SEKE only took 136 seconds, which is more than 60% reduction in time cost. While for EndStatus, the reduction is not that much, but SEKE is still more efficient than EMMA. For RQ2, although the number of generated blocks by SEKE is greater than EMMA, which may be because of different standards used in categorizing blocks, there's only slight coverage difference in terms of the percentage of executed blocks. So we think SEKE and EMMA are close in terms of precision based on this observation. Here shows the results of applying retest-all and Redroid on Identify. For RQ3, we found that for Identify, while retest-all selected all the 206 test cases, Redroid selected a range from 36 to 171 test cases uh, that achieved 16% to 83% reduction in the number of selected test cases. Moreover, we find that the number of selected test cases varies for mutant versions with the same number of changes. For example, for mutant versions v0 to v5, where only one change statement is involved in each mutant, Redroid selected 5 different numbers of test cases for each version. Despite that, unsurprisingly, we found that overall, the more changes got involved in the mutants, the more test cases were selected. For RQ4, we found that for Inedify, there was 4 seconds overhead of applying Redroid due to static impact analysis, coverage generation, and test selection. However, compared with the execution time of all the test cases, which is 134 seconds, the overhead is not that much. Moreover, we see that when a Redroid is performed, due to the reduction of the number of test cases for re-execution, the time cost for re-executing those selected test cases is also reduced. Even when the overhead is counted, Redroid still achieved reduction in time cost, and the biggest time reduction is 79% for version 4. So similar pattern of results can be also found for AND status. To conclude, we presented a bug study based on 10 real-world Android apps from Google Code Repository. This study showed that regressions exist for Android apps during evolution. Motivated by the study, we introduced Redroid, a new approach to regression test selection for Android apps. Given a test suite that was performed on the original Android app and 2 versions involved in a change, Redroid identifies a subset of the tests that must be re-executed to test the new Android version. We conducted experiments to evaluate our approach Redroid, and experimental results show that Redroid can significantly reduce the number of tests for re-execution, as well as the time cost for re-executing the selected tests after an Android app is modified. Thank you very much for your attention. Please feel free to contact me if you have any questions or comments.